No, it's just a recording. Yeah. Just so you're not like that.
Excuse me. Okay, so I guess we can start. Welcome also to the physical program, which is exceptionally on a Thursday. Thank you all for noticing that and for still making it. It's our great honor and pleasure to welcome today Stephanie Reich, who is a professor at the Free University of Berlin. There's 3 universities at Berlin, and she's from the free one, which is the youngest one. Stephanie got her PhD also at a different university in Berlin, Technical University of Berlin. And after that, did a postdoc in Barcelona, was then a fellow at Cambridge University in the UK, Cambridge, UK. And then assistant professor at MIT, and then accepted a full professorship at the Free University. She has received a number of accolades and prizes. Maybe some of the most notable ones are like ERC Starting and Consolidator Grant, so the European Research Council grants, they're very competitive in Europe. She got Excellence for Teaching Awards, and it's a great pleasure to have you here today. And you're going to talk to us about supercrystals of gold nanoparticles and the unique coupling to light. As a spectroscopist for a long time in my career, I should talk about light matter coupling, think plasmonics. So we're looking forward to that a lot. Welcome.
Thanks everybody for coming, and thank you very much for the invitation. It's a very kind introduction, Matthias. It's actually my first scientific visit here at Brown University, but it's not the first time I'm here because my husband is actually a graduate from Brown before we met, that was. And he took me here when we were visiting New England. So he showed me his former lab in the basement, and then he showed me the grad students bar. And then we had a drink there, and he said, okay, now I had seen where he spent 90% of his time. Yeah, so it's great to be here, and I had really very nice conversations and discussions with people this afternoon. And now I want to show you some of our research, which deals with supercrystals that are made out of gold nanoparticles. So they are shown here in a kind of sketch, so you should envision that each of these little spheres in the face-centered cubic crystal is a gold nanoparticle, not a gold atom, as you would normally expect. And up here, there's an image taken with a scanning electron microscope where you can see these crystals as they look in real life. And I want to talk about them as a really exciting material, exciting artificial material that we can use, for example, for enhanced spectroscopy and for photocatalysis. But I want to convince you that they also question our fundamental understanding, what actually constitutes matter and whether photons are part of matter, what light is in relation to it. So if you think back to the interaction between light and materials that actually started with this publication from Paul Dirac almost 100 years ago, when he went to calculate the absorption and emission of light by an atom using quantum mechanics. So that was the first attempt to use quantum mechanics to tackle this particular problem. And one of the things that he did immediately or kind of implicitly in this publication, and that we've done since then forever on, was to separate this problem of light absorption into a part that describes the atom. And I'm going to show you many of these sketches where I show an excitation of either an atom or mostly a nanoparticle in this talk as a kind of a dipole excitation here. So the atom on the one hand and the photon coming in on the other hand, and these were two separate systems. And then he introduced like matter interaction as a perturbation. So the question is, why is it actually justified? Why can we do that? Yeah? And at that time, the answer to this question appeared to be straightforward, because we can switch off light. Yeah? So we can make it dark, and then there is no light And so that justifies the separation. But by now we know that there are also vacuum fluctuations of the electromagnetic field. So even if you make it pitch dark, their photons are still going to be there. So we are kind of lost this justification. The second justification, and that's actually the correct one for this particular problem of atom absorption, is that light-matter coupling is inherently extremely weak. You can, in this approximation where you describe the excitation of the atom as a dipole and have it interact with a photonic mode of a certain mode volume, you can actually write down an analytic expression for the strength of light-matter coupling. So it depends on a bunch of constants that you know, like the charge of an electron and the dielectric constants, the mass of the excitation, so in this case an oscillating electron, the oscillator strength of the transition, so that essentially counts the number of electrons that you will be able to excite, and the mode volume. And if you plug in the numbers here, for an oscillating electron, you will find that light-matter interaction is 0.6 eV per the square root of the mode volume. And if you describe the mode volume as a photon flying through space, with a certain interaction cross-section and a certain kind of lifetime for the entire pulse, you will find that light-matter interaction in free space is less than 10 to the minus 6 eV. So compared to the transitions that you're looking at that are on the order of eV, that's really a very tiny quantity, and you can safely introduce this as a perturbation. So that's how things stood for a very long time, but then people became kind of unhappy with the fact that light-matter interaction was so tiny, and they thought, is there a way to increase it? And the idea was, let's reduce this mode volume here and come up with something that is a photonic cavity. So where you take two mirrors, it could be, for example, silver mirrors, and you now have your excitation inside this photonic cavity, and the photon is kind of held in place. Yeah? So it reduces its mode volume, it increases the interaction time with the dipole. And if you consider a mode volume for a photonic cavity, so something that's bound to be lambda to the power of 3, then you will find that you can increase from 10 to the minus 6, you can go to 10 to the minus 4 light-matter interaction in this type of photonic cavities. So this is still pretty weak interaction, but even for this still weak light-matter coupling, you can already see an effect of the light field on the properties of materials. And one of the most well-known ones is a Purcell effect, and it tells you that the spontaneous decay of an excited emitter will depend on the light-matter interaction strength. So here are two very famous examples. This is kind of the defining experiment that people will always show when they talk about this. So here are quantum dots that are put into a cavity. The cavity looks a bit different. It's than two mirrors, but essentially it's exactly the same concept. And if you have these quantum dots in free space, this is the lifetime of their light emission. And now if you put it inside the cavity and you make the cavity resonance with the transition of these quantum dots, you can see with the resonance with these quantum dots, you can see that the decay is much faster. And you can also slow down the decay by making it non-resonant with the cavity and so forth. And a very similar idea is shown down here. Here you have a thin film of molecules on top of a silver mirror. And here is the lifetime measurement again. So they have a lifetime of 600 nanoseconds. And then you take a cube, a metallic cube, and place it on top so that you make a cavity between the bottom layer of this cube and the substrate where the molecules are put on. And you can see that the lifetime of the emission decreases drastically to less than 1 nanosecond. And that comes from the increased light-matter interaction that you obtain thanks to reducing the mode volume here. Now, you can try to further increase light-matter coupling by making these cavities smaller and smaller. And if you go to so-called sub-wavelength cavities, where you confine the light more than you would normally think you're able to do, so you can do this with plasmonic structures, you reach a regime where the light-matter interaction strength becomes comparable to the losses that you have in your system. And if you're in this regime, you will call it strong light-matter coupling. And then something very interesting happens. Instead of having really a separated photon and materials excitation, the two of them start to interact and build a hybridized state. So instead of having the photon and the dipole in resonance, they will hybridize and you will get a lower polariton and an upper polariton, and the energetic separation between the two is known as the Rabi splitting, and it corresponds to twice the interaction strength for light-matter coupling in your system. So these states are really of mixed character, and here is a very nice experiment where people showed that. So they prepared atoms that they sent through one of these cavities, and when the atoms got out, they probed whether they were more of atomic character or of photonic character. And then you could see that with time, the state really oscillated between being material, so dipole type in character, or photonic type in character, and the frequency of this oscillation corresponds to the to half the splitting between the upper and the lower polarity. So it's not just a way of thinking and talking about hybridized light-matter states. You can really show that they are of this nature. So what we produced here is now really a new system. It is a coupled light-matter system where the excited states are totally different from the ones we had in the beginning. And you know, people speak about cavity molecules, for example, and these are excitations of cavity molecules and so forth. But up to now, the ground state of the system remains still totally unaffected by light-matter interaction, and also the coupling is still so weak that you can use perturbation theory to describe it. So nevertheless, there are many exciting applications for strong light-matter coupling, and I just want to flash one of them, and that is the Bose-Einstein condensation of these polaritons that you produce. And here you can see that with an increasing pump state, with an increasing pump fluent, the states becomes more and more confined in energy and also in reciprocal space. And this is a key signature of a Bose-Einstein condensation. And one can then take this to build lasers. There are also discussions that you could change chemistry, photochemical reactions using strong light-matter coupling. There should be effects on superconductivity and so forth. I mean, many of these ideas are really controversial, and not all the experiments are really conclusive. But I think it shows that this is really a deeply inspiring topic and very interesting thing to think about. Okay, so people were still unhappy with the 10 MeV here. So that was, I mean, it was strong light-matter coupling already, but it was still pretty weak. So for example, you could not really deal with it at room temperatures. You had to go down to cryogenic temperatures. So they thought, let's further increase light-matter interaction. And kind of the key trick to do that is to put not just one dipole into the cavity, but to put many of them into the cavity and then look at the interaction of this collective ensemble with the photonic cavity, and that will increase light-matter interaction by a square root of n, where n is the number of particles that you put in. So in the example that I drew here, it would be twice as much, and of course you can put in many, and then you reach regimes of light-matter interactions that are 100 MeV. So that's room temperature, and it also starts to be a sizable fraction of the total excitation that you are looking at. So in the beginning, yeah.
Why square root of n?
Where the square root of n comes from?
Mm-hmm.
It is essentially, I mean, it comes from a similar, so you will have n times the original oscillator strengths in here, yeah. And if you call all these G naught d, that's the G naught d here, then you have the square root of n that goes in front of this expression.
There's no, so when the photons bouncing between the dot and the mirrors,
yeah,
the location of those dots don't matter.
No, they don't matter.
Oh, because the
And-
wavelength is much bigger.
Yes, yeah. And a crucial approximation that's always made and that we have to drop at some point is that these dipoles don't interact.
Okay.
Yeah. So this expression you get if you consider them to be non-interacting.
So there's no interference effect here between them. Okay.
Okay, so in the beginning this was done, for some atoms in a cavity or maybe some molecules in a cavity, but then people kept going and they pushed more and more stuff into the cavities until you ended up in a situation where you really had the entire cavity filled up with material. And I just brought two of these examples, there are really hundreds, thousands by now, to show you examples of that. So this here is a film of mercyanine molecules inside a silver cavity and outside a silver cavity. And mercyanine has a very prominent absorption in the visible energy range. So this is when you look in the part of the sample where there's only the bottom cladding but no top cladding. And then when you go to the cavity, it splits into two peaks, and they correspond to these lower and upper polaritons that I've introduced before. And here's another example. This is now not for optical excitations, but for vibrational modes. So this is hexagonal boron nitride and a cavity that's solidly filled with hexagonal boron nitride. And again, the splitting is a bit shown differently here, but you can see that there is a separation between these two branches. This here is the lower polariton branch, and this here is the upper polariton branch. And there is a way to select the wave vector in these type of experiments. So we looked at these things, and what we started to ask ourselves is whether it still makes sense to use cavities for these kind of experiments. Because originally we had the cavity there to keep the photons in place so that they interact longer with a single molecule. But if you take a material, if you consider an infinite crystal, then your photons are going to be inside and will also perfectly overlap with the material. So there's actually no need to resort to a cavity in order to increase light-matter coupling. You're not achieving very much with that. So our idea was to look for a crystal and to design a crystal in such a way that we would get ultimately strong light-matter interaction. Yeah. So here we have a crystal, and we kind of considered this expression that we had for the light-matter interaction strengths. And okay, we didn't really know what we were doing with the mode volume here, but we had the feeling that we were increasing it very much. So the idea was, in order to get strong light-matter interaction, we should maximize the oscillator strengths of the individual building blocks. We later found out that this way of thinking was actually not fully correct, because loss in mode volume is not that important, but that's, that was our starting point for the idea. So if you look at oscillator strengths of things like organic molecules, so the benzene molecule shown here, or a quantum dot, so it's a cadmium selenide quantum dot, you will typically find that they're on the order of 1 to 100, because that's the number of electrons that you can excite. We decided to go to gold nanoparticles instead, because their oscillator strength is many orders of magnitude larger. And I want to give you a brief introduction into gold nanoparticles and their plasmonic properties. I heard some of you talking about listening so often to plasmonic talks, but you need to get the introduction again. The optical properties of gold nanoparticles is something that mankind has really used for many centuries. They have the ability to very strongly absorb and scatter light. And if you look at these old church windows, and this here was the one in Notre Dame, it unfortunately was lost in the big fire of Notre Dame, then a very bright red color that you have in these church windows, they come from gold nanoparticle inclusions inside the glass. Yeah. And the way in which these gold nanoparticles interact with light is kind of illustrated here. So imagine that you have a gold nanoparticle and an incoming photon. And the photon is shown as an oscillating electric field as a function of time. And when the electric field is pointing upwards, you will have the separation of the electrons and the kind of core, the positive core. And if you wait some more, the direction of the electric field is reverted, and then also the flow of all charges is in the opposite direction. And you can imagine if you drive such a system, if you do it with the right frequency, you will hit its eigenfrequency and you will get a resonance. And that's called a localized plasmon surface polaritron resonance. And you can also consider these plasmon polaritrons, or these plasmons as they're typically called, as excitations of your gold nanoparticles. And there are some ways to write down the expected frequency in a certain limit. It's a quasi-static limit. And there will be a dipole type of excitation that is going to be optically active and will very strongly interact with incoming light. There are also higher order modes like these quadrupole modes and this hexapole here. For the rest of my talk, I'm not going to consider them. We've done it. If you want, you can ask me about it, but I will exclusively focus on the dipole excitation because it shows kind of the essence of the entire thing. So the nice thing about these plasmon resonances is that they are widely tunable, for example, by the material that you use. And here is a comparison between the absorption coefficients that you would get for a gold nanoparticle and the absorption that you would get for a silver nanoparticle. Yeah, and they're shifted because the dielectric properties of these two materials are different. You can also change the shape. And here's the simplest changes, namely if you make a little rod out of the spherical nanoparticle, then the longitudinal mode that oscillates in this direction will move to smaller energies. And here's a collection from Naomi Halla's group at Rice University, where they produce nanoparticles, metal nanoparticles made of different metals and different sizes and shapes, and you can see how beautifully you can shift the colors around. So one of the key features of these metal nanoparticles is that if you excite a plasmon in such a metal nanostructure, it will produce a very strong optical near field close to the metal surface. Yeah? And this here is a simulation where you plot the E field intensity related to the intensity of the incoming light that you use in the simulation in order to excite this plasmon resonance, and you can see that there is an enhancement of an order of magnitude at least. And then you can start further playing around, for example, by combining two of these nanoparticles, and if you shift them close enough together so that the electric fields overlap, you will get an excitation that has a very strong hotspot here in the middle. And you can describe this really with the same concepts of hybridization that you use for the formation of diatomic molecules, but only with the optical excitation this time instead of the electrons. So you can say I have a nanoparticle here, it has a little dipole that's indicated here with blue and red, and I have a second nanoparticle, and if I bring them close together, their dipoles interact, and then can I line them parallel along the axis, or anti-parallel along the axis, or parallel perpendicular to the axis, or anti-parallel perpendicular to the axis. And because of the interaction of the optical near fields, all of them, oops, where's my pointer there? All of them will have slightly different excitation energies. Yeah, so you can build up first a dimer in this way. This idea was put forward by Nordlander exactly 20 years ago. And then people started to build more and more complex structures, hexamers, pentamers, octamers, and whatever, and tried to construct special optical excitations and resonances using these concepts. Okay, so we said, let's take this idea and apply it to crystals. Yeah. So let's take such a crystal of gold nanoparticles and describe them theoretically by putting a dipole into each of these nanoparticles and then let all of these dipoles interact. So we're kind of deviating from what I showed you for the cavities, where people say they don't care about the interaction between the dipoles. We now deliberately look at the dipole-dipole coupling. And if you do that, you can write down in Hamiltonian for the plasmons, and you will get a dispersion for the plasmons inside this supercrystal, it's called. So a crystal made out of these nanoparticles. And I want you to focus on the gamma L direction here, because that is the one that we are later on also going to use in experiment. And there's one longitudinal plasmon where the electric field is polarized along the propagation direction. And it's important to realize that the electrons that kind of make up this excitation, they're all confined and localized to each nanoparticle. Yeah, so they cannot move, in contrast to a bulk metal. They cannot move through the crystal, but the plasmon is able to propagate excitation through the entire crystal. And this longitudinal or such a similar longitudinal excitation you would also get in bulk gold. But what you would not get is a transverse mode. And in these supercrystals, due to the fact that the electrons are bound here to the nanoparticles, we also get a transverse plasmon excitation. Okay, now this simulation was considering only the dipoles in the nanoparticles, but I did not consider interaction with photons, with far-field photons. Yeah. And
how large are the nanoparticles?
So right now they're just dipoles. Later on they're going to be between 50 and 100 nanometers. But this is, I mean, okay, so the size, if I take this away, then this is true independent of the size of the nanoparticles. So it's really just
so
the
it's
dipole.
the coupling that's giving you that energy scale.
Yeah, yeah.
Thank you.
Okay, let's put the photons too, yeah? So now the dashed yellows is exactly the same dispersion as I had here. So these are only the plasmons or only the dipoles. And the dashed blue is the photon dispersion in free space. Nothing fancy with it. You can see that for the longitudinal mode, essentially nothing happens. And that's not surprising because photons are transverse excitations and they will not couple to a longitudinal excitation. But then when you look at the point where the transverse plasmon and the photon cross, you can see that there is a huge anti-crossing that extends over several EVs. So this is the coupled state after I put in the photons, the coupled lower polariton and the coupled upper polariton. So this corresponds to kind of this sketch that I showed you a couple of slides ago, only that the splitting is way, way larger than it was in the first examples. And we extracted here the Rabi splitting and the light-matter interaction strengths. And the Rabi splitting is 8 eV, so the light-matter interaction strength is 4 eV. The frequency of this transverse plasmon is roughly 3 electron volts, so we neglect the small dispersion that you can see here. So if you look for the so-called reduced coupling strength, which is the ratio between G and omega T, you can see that it is larger than 1. And this is a regime of light-matter interactions. It's called deep, strong light-matter coupling. And it means that if you think back to your Hamiltonian we started from, where we said, okay, we have the atom and we have the photon, and then we have a perturbation, and that's the interaction. Now, all of a sudden, this perturbation is actually stronger, larger than the two excitations we started from. So, and this is, I already said it now, essentially, so these were the regimes we discussed before, yeah, so the weak coupling regime and the strong coupling regime, there you had a change in the excited states of the material. And now we moved into the so-called regime of ultra-strong and deep-strong light-matter coupling, where the interaction strength is comparable or even larger than the bare excitation frequency. And what happens then is still you have change in the excited states, but at some point you should also expect the ground state of your system to change, because you can no longer deal with a separated Hamiltonian. We were also able to develop an analytic model that kind of describes this situation, the 3D crystal, yeah, very in a similar way of thinking as we did it for the single excitation in the cavity. And the expression for light-matter interaction is actually the same as we have in the cavity, except that the mode volume of the photon gets replaced by the volume that this dipole occupies. Yeah, that's something like the unit cell of the crystal that we consider. And because you can confine electrons and also phonons and so on much better than you can confine photons, the interaction that you get in crystals is actually much larger than what you had for cactus. Okay, so far for the theory. Now let's see whether we can actually get the stuff. And for that, we started to team up with collaborators from the university in Hamburg. And I really want to mention Florian Schulz here in particular, who developed this entire concept of nanoparticle synthesis and supercrystal growth. And what he was working on when we met was to grow gold nanoparticles with essentially the standard techniques that people use to grow them, but he tried to make them bigger and more uniform. Yeah, and in order to achieve that, first he was very careful in really controlling the conditions that he used for growth. And also he used a new type of ligands to stabilize these gold nanoparticles so that they don't agglomerate in solution. And the ligand is essentially a polystyrene brush that he attached to the surface of the gold nanoparticles. And these polystyrenes are great for stabilizing the gold nanoparticles. They're also, he was also able to ensure really a extremely high uniformity of the gold nanoparticles. So this is a TEM picture, and you can see that they're all nice and round and exactly of the same size. And also the ligand promotes an hexagonal order when you dry these gold nanoparticles on a liquid surface. So this is how these monolayers are produced. That's kind of shown here. They are grown at the interface between two liquids. So you have one liquid down here where the gold nanoparticles cannot be solved in. And then you put toluene with the gold nanoparticles on top, and you slowly let the toluene evaporate. So the concentration of the gold nanoparticle keeps increasing. So at some point they start to spontaneously crystallize and form, for example, such monolayers, bilayers, tri-layers. I get to your question in a second. And if you spend enough time on them, even nanoparticle crystals. Yeah, so these are now, is an SEM image where you see a little lamella of such a gold nanoparticle crystal. And if you look at the edge, you see the two facets of 111, yeah, with their characteristic hexagonal closed packing. This was for 60 nanometer gold nanoparticles. By now, he increased the size of the nanoparticles to 130 nanometers, and they can still crystallize in these beautiful supercrystals. Yeah, I had a question.
I have two questions. So previous slide, and some particles are darker than the others.
Yeah.
Why?
That is essentially different concentrations that he used.
No, here.
There. These are the different facets of gold you're looking at. So they are oriented slightly differently. Yeah, okay. And whether you look down the 111 direction or 112, that makes a difference in the contrast.
So this misorientation of the facets play no role whatsoever in the...
No, they're too big. Yeah.
The wavelength is too big. Okay.
Well, the gold nanoparticle is too big. So, I mean, if one thinks about small nanoparticles, then they have facets. Yeah, like I discussed today. Mm-hmm. But if you go to these very large gold nanoparticles, and 50 nanometers might not sound large, but for nanoparticles it is very large, then they're really perfectly spherical. Mm-hmm. But you can still see the distance as a difference in contrast because the atoms are arranged differently when you look through.
The second question: if I deliberately create an edge dislocation here,
yeah, and
what happened to the Clariton modes?
So in such a model, we can discuss it. Maybe
I'm just wondering what happened to the anti-crossing.
I think it would remain in place. It is so the anti-crossing is mainly a function of the packing density, and not so much of the crystal structure.
But it depends on the K, right? So there will be a misorientation of the K.
So I will later show. I will later show the signatures that you get in optical spectra from these polaritons. and they will broaden. When the crystal is less oriented than this one, they get broader. We actually have done that experimentally as well. So yeah, now let's see how we can measure these polaritons I spoke about and the optical response from this supercrystal. And the experiment is really goddamn easy and straightforward. The thing that we do is we measure at the same time transmission and reflection from a gold nanoparticle film. Yeah. So we take two microscope objectives. In between them, there is a gold nanoparticle film. And then we shine in a light from a supercontinuum light source, and we measure the transmittance, and we measure the reflectance. And then in order to calculate the absorption, we calculate 100 minus reflection minus transmission, and that will give us the absorption strength. Now here are some view graphs to give you an idea how these look like. If there are only very few layers, so this is the number of layers, you can, these gold nanoparticles are actually very colorful, the supercrystals. Yeah? And you can nicely count the number of layers in transmission up to perhaps 5 or 6 layers. You also see it in reflection. And the place where you see it best actually is in dark field spectroscopy, because there such a layer gives you very little contrast, but then when you have a step from one layer to the next, there's always this scattering line at the edges.
What happened to the monolayer?
The monolayer is not, it's just a part of the crystal where there is no monolayer. The monolayer would be a bit lighter blue, but it's just a picture that we took on the crystal, and there was no monolayer. But we know the different colors, so we know that these are 2 layers and not a monolayer. Okay, now here's a little view graph where I tried to explain how these excitations then actually look like. So these are simulations, these are not measurements, and we start from a bilayer. So we just have one layer of these hexagonal packed super nanoparticles and the second one. And then the only excitation you get is where all dipoles look in one direction, in one layer, and in the other direction, in the other layer. Yeah, that's the only thing you can do. Now, if I add a third layer, I can have one where the dipoles in the lowest layer look in one direction, and there are no excitations in the middle one, and in the topmost they look into the opposite direction. But you can also have one where you have alternating dipole directions in each layer. You add one more, you get another peak, and so on. And in fact, the entire thing is just an open cavity boundary condition where you get standing waves whenever an electromagnetic field is able to enter with a maximum of the field strength here at the interface, and also, again, able to leave with a maximum field strength of the interface, at the interface. And here are experiments where you can see a very similar behavior. For the bilayer, you have a single excitation, then you have 2 peaks, and they move in energy because you make the crystal thicker and thinner. So the boundary conditions, the wavelengths that's compatible with the boundary conditions will change slightly. And then we had parts of our gold nanoparticle supercrystals where in SEM we saw that we had these kind of terraces where the layer number changes always by 1. And you can find them back in dark field microscopy. And it starts here from 4 layers. Here's this large part, and then 5, 6, 7, 8, 9, 10, 11, 12, and so on and so on, all the way up to 23. And we measured the reflectance, all the reflectance spectra from all these different layer numbers. And this here is what you will get. So this is the thickness of the crystal. Here you have the excitation energy. And you can immediately see that there are some characteristics in this reflection measurements. One is that you have here this range of very large reflectivity, almost equal to 100%. And that corresponds, I think I forgot, unfortunately, to say that. Let me go back. That corresponds to the energetic separation between this lower and the upper transverse polaritons. There you have a large part where there are no electromagnetic states inside your crystal. And then light is not allowed to enter, and you will get 100% reflectivity. the extent of the energy was not as large as we expected from theory, and the reason is that at roughly 2.3 eV, you have intraband transitions in gold, so the description as a plasmonic material does no longer apply to these energies, and everything breaks down and you get very strong absorption, and that's it. And underneath this polaritonic band gap, there are these kind of fan-like dependencies of these lines on the layer thickness, and they correspond to these standing waves that we have inside our crystal. And you can use them in order to construct a dispersion where you plot the energy of the excitation that you get off here versus the inverse wavelengths, which corresponds to the wave vector across the growth direction we are looking at. Yeah. And from that, we got these data points here. And if you remember the calculations we had before, what we are looking at is this transverse plasmon polariton branch down here, and we can fit it to a Hopfield-like of expression of a polariton, and from that extract light-matter interaction strength almost 3 eV, and the ratio between the reduced coupling strength, the ratio between light-matter coupling and the original frequency. And we were very proud to see that we are indeed in this regime of deep, strong light-matter coupling. And we did that for many different sizes of gold nanoparticles and different distances. So we varied the packing density, and thereby you can tune light-matter interaction from roughly 1 to almost 2. And then here's one of these famous view graphs where you show what everybody else did and how much better you are than what they attempted. So what's plotted here is the, unfortunately it's overlaid here. So this is the reduced coupling strength. Yeah? So above 1, we have this regime of deep, strong light-matter coupling. And down here is the absolute coupling strength, so how large it is. And you can see that we are the highest in reduced coupling strength. And we are also the highest in the absolute coupling strength, which is very important because this is really, it means we don't have to go down to cryogenic temperatures and so forth in order to observe these exotic states.
So the other dots are other plasmonic materials?
No, these are, many of them are organic crystals, organic crystals in cavities typically. And then these orange ones, these are semiconductor nanostructures, so gallium arsenide mainly, and these here are Landau polaritons. So that's, but you can see that they barely stretched deep, strong couplings. Okay, so and then from there on
so the coupling also, do we know whether they actually scale as the square root of the volume, like you said before that for the model that you had?
That's a very nice question. We have never looked at this because we actually did it vice versa. I mean, we first did the experiment and then later I will look at these things. So then from there on we started, to look at different things related to these gold nanoparticle supercrystals. One set of experiments and research directions looks into confirming the surprising physics that was predicted for deep, strong light-matter coupling. And the example that's shown here is that the Purcell effect, remember I introduced it, that corresponds here to this increase at low reduced coupling strength. If you go all the way up to ultra-strong and deep, strong light-matter coupling, the Purcell effect should saturate and turn around. And the reason for that is that you have at very high coupling, you get a decoupling of light and matter excitation. So they will be separated in energy and they will also be separated in space. Yeah. And we were able to confirm that, but I'm not going to show this in detail. We also started to look at binary supercrystals. And if you look closely here, you can see that this is a cubic structure and is actually the cesium chloride structure that we grew by using gold nanoparticles of different size. Instead of just having one that will always give you FCC, we started to use 2 types of nanoparticles and also developed the theory for that. So what I want to look at are these 2 examples down here, and namely surface-enhanced Raman scattering, surface-enhanced infrared absorption, and also surface-enhanced catalysis that rely on the structure of the electromagnetic, or in fact the electric field inside the gold nanoparticle supercrystals. So let me show you what we mean by that. So here's a simulation of how the electric fields look like inside the gold nanoparticle supercrystal. And it's it's infinitely extended, so these are like photons in free space, except that the electric fields, is it my time? That the electric fields have this, consist of this series of hotspots. Yeah, you see that in some places the electric field is extremely strong. The different colors come because you have the standing waves inside the crystals. The white parts is where the gold nanoparticles are, but this is really the outcome of the simulation. We did not put them to zero, they are white because there is no electric field inside the matter. And we thought, okay, so this is a nice system to use in order to place something in this hotspot and use it to increase optical processes. Yeah, and this is, in fact, let me skip this one here. This is, in fact, a very well-known application of plasmonic systems. This is surface-enhanced or plasmon-enhanced Raman scattering, where you take a molecule or whatever you want to do your Raman experiment on and put it into such a plasmonic hotspot. And here's an example of what happens then. So down here is a Raman spectrum of 10 to the 6 molecules, and it's increased by a factor of 800, and you can see some peaks. It's a rhodamine spectrum. And here is the same spectrum coming from a single molecule when it was placed in a really very strong plasmonic hotspot. So this amounts to 8 orders of magnitude increase in the scattering intensity, and people have the hope to use it for single molecule detection and so forth. But one of the serious drawbacks of surface-enhanced Raman scattering is that it is extremely sensitive to the placement of your molecule. If you just place it 5 nanometers to the right or to the left, this spectrum here will be gone. So you cannot use it as a very reliable sensor or detector to find something. And our hope was that because we have so many hotspots inside our gold nanoparticle supercrystal, we should be able to really get a very nice, reproducible, and stable enhancement of the Raman scattering intensity. And here is a scan where we start from a single layer of these gold nanoparticle supercrystals, where we cannot excite this hotspot, we cannot couple to the far field. And then we go to a bilayer, and out of a sudden we have the excitation of these polaritons. We get the very strong hotspots inside, and you can see very nicely how the Raman intensity increases. But then if we keep going, the Raman intensity really stays the same. And you can scan over large areas of your sample, you can change polarization and so on, and it will not. So then we looked also on that we can confirm that these absorption peaks that come from the polaritons, that they are really behind the enhancement we see in the Raman experiment by using different wavelengths and so forth. And you can do something similar in infrared absorption. But what I want to show you now at the very end of my talk is that you can also use these crystals in order to produce enhanced photocatalysis. So this is a reaction where you decompose formic acid in order to produce hydrogen. Yeah? And it is really thought, it's first a model reaction that people like to use in chemistry, and it is also thought that formic acid might actually be a viable source of hydrogen for future technologies. And here are the gold nanoparticle supercrystals, and if we use them as kind of catalysts, they're not active, but if you use them as kind of catalyst for the formic acid decomposition, you get this response here, and it does not matter whether the light is off or on. Yeah? And then here's a gold nanoparticle supercrystal, or it's actually monolayer only, where there are a platinum, 2 nanometer platinum nanoparticles in the voids of the supercrystal. And platinum is a known catalyst for this type of reaction. So already in the dark, you can see that the reaction yield increased by a factor of 2. And then when we switch on the light, there is a further very strong increase in reaction. And I mean, if you've heard about plasmon-enhanced chemistry and catalysis and so on, people always discuss whether there are hot electrons that are kind of created and extracted from the material. I just want to stress that we do not think that this is a mechanism in our system. It is simply the fact that you concentrate the electric fields very much. So here's a simulation where you can see the concentrated field as the places of the platinum nanoparticles. So you do a catalytic reaction with a much higher field strength as if you would crank up a laser in the experiment, but that can be done it was done with a light source that mimics solar light. And the idea, of course, is to use solar radiation in order to do this, to use this for hydrogen production. So this paper appeared today, and Matthias was so nice to print it for me. And tonight I'm actually meeting two of the co-authors because they're at the conference as well where I am, so we can have a beer. So thank you, Matthias. Okay, so I'm almost at the end of my talk. I just want to say again, I mean, in the beginning, we started from the idea that it would be a good approximation for atoms and also for materials to separate them into a part that describes the material here that contains the electrons, the ions, and also their interaction. And a second part that contains the photons, the coupling of the electrons and the photons, and also the coupling of the ions and the photons. And that, as I said, goes back to this very nice paper. But you can see that in the case of our system, the energy of the interaction strength is of similar order of magnitude as all the other energies that you have in the Hamiltonian. So, in fact, what we should do in order to see light as an external perturbation to our material, we should actually regard it as part of the building blocks that make up matter. And you might say, okay, no, you constructed such an artificial crystal in order to produce very strong light-matter coupling and so on. So why is that important? It's important because when we went back into the literature and looked at many different excitations that we have in crystals, excitons, vibrations, infrared active vibrations, plasmons, and so forth, and plotted their light-matter coupling strengths as a function of the excitation frequency, they will be in the ultra-strong or deep-strong regime if they are in this gray shaded area. And what you can see is that this is actually a very common phenomenon for many crystal excitations, that they have an extremely strong coupling to light. It's just something that we haven't really realized so far. So that brings me to the end and to the important slide where I want to acknowledge the people who did the work together with me. So this entire field of research, this called nanoparticle supercrystals, was started together with my former PhD student, Niklas Müller. He was then in UK and is now back to Berlin, but at a different institute. So Matthias mentions that there are 3 universities. There are 30 research institutes also in Berlin. So right now in my group, the PhD student, primary PhD student working on this is Sabrina Jürgensen. In particular, she did a very nice catalysis work together with people from the LMU in Munich. So Matthias Eran was here the defining student. The theory support comes from the group of Eduardo Barros at the University of Fortaleza in Brazil. The University of Hamburg is where the synthesis is developed, and I already mentioned and want to stress again the great input of Florian Schulz. And then the surface enhanced infrared absorption experiments that I skipped were done in the group of Joachim Heberle, also at our university, Freie Universität in Berlin. And yeah, with that I bring up my conclusion. I don't want to repeat them, but I want to thank you very much for your attention.
Thank you for an exciting talk. Sure, there must be questions. Yes.
2 questions. First one is about supercrystal formation.
Yeah.
So I wonder why you use the polystyrene polymer as a coating for. Usually polymer we try in order to get a super lattice. We don't use polymer because it's really hard to control polymerization degree. That you don't have a uniform.
It's not polymerized. It is so these polystyrene brushes are put on and they kind of they're just pushed into each other.
But the brush, you still have a longer brush, if it's shorter brush, they can be really hard to form super lattice.
So this
chemical process. I just wonder why they choose polymer.
I mean, the polystyrene was mainly used in order to stabilize gold nanoparticles because the typical, the CTAP and so on that you use normally to stabilize gold nanoparticles,
But
if you go to larger ones, they don't work.
yeah,
very
the
well.
key part is the coating uniformity, right? So in order to form a supercrystal, you need a coating to be uniform in order to form this structure. If it's coating, you have a relax, the longer brush, shorter brush. That can be really hard to form super lattice structure. I wonder, do you think it's
I don't understand your
the
point
coating, the
entirely.
uniformity. In order, you have a hard sphere, you have a
Yeah.
softer layer,
Yeah,
right?
yeah,
Softer
yeah.
layer needs to be uniform in order to form this super lattice structure.
Yeah. And I mean, they are uniform on the length. So these polymers, there are 2 nanometers in length. The point is that the nanoparticles are really huge compared to quantum dots or other particles that have been used in order to produce superlattices. Because they are so large, the variation in the length of the polymers is not so important anymore.
So only spherical repulsion is used.
Yes, absolutely. Nothing else. I mean, we now started to talk about charging using charged brushes for these gold nanoparticles because that would help in producing non-FCC structures. So, for example, in order to promote the sodium chloride structure, cesium chloride structure, if we had positively and negatively charged particles, that would, of course, be very beneficial. But we haven't started with that.
Yeah, second question about the HER catalysis. So it's really plasmonic. So the platinum, the quality compared to gold, platinum quality seems like, clearly as a catalyst part.
Yeah.
It's really hard to control that part. I wonder, is that the light enhanced? It's really a trapping proton. You do use the formic acid, right? Formic acid, you have a lot of proton there. With light, with the polaron formation, you have a negative charge. They can attract a lot of protons. So locally, concentration is going to be higher. So then you're going to see the enhancement. It's just a chemical effect, do you think, or is it just a light effect?
I mean, one thing that's shown here that I haven't spoken about, that is a dependence of the catalytic activity on wavelengths. Yeah, and these points here are measurements of the reaction rate as a function of the production as a function of wavelengths, and that is compared with the calculated enhancement of the electric field inside the supercrystal. Yeah, and you can see that it very nicely follows the field enhancement that you see inside these gold nanoparticle supercrystals. We also had controls, but it's super difficult to get a control where you take out the gold nanoparticles. I mean, we could take out the platinum nanoparticles, obviously, but to take out the gold nanoparticles and only have the platinum kind of distributed on a surface like that is, basically impossible to do. Yeah. We had a control where we just spread platinum nanoparticles on a surface, and then there was no difference between light on and light off. There was a difference between light on and light off, but it was much smaller than what you see here in the gold nanoparticles.
Yeah, so I saw you, for yourself, for example, just the particles, you use a really large gold particles.
Yeah.
Right? And I was going to ask about the length of the polymer. You said it's about 2 nanometers.
Yeah.
Yeah.
But that can be varied, and then the distance between the gold nanoparticles will change.
Yeah, so whether you're like use really small gold particles, for example, into the same structure, and whether that's going to affect your coupling effect.
Very small we did not do, but we did small ones, I think down to 12 nanometers, that was the smallest one. So this year it's only down to 25. So this year is between 25 and 60. And the 20
the same ligand, right? So everything is the polystyrene ligand.
It's the same type of polystyrene ligand, but different weight sometimes. Yeah. But there's also a very nice paper where Florian discusses these things. So here's this Nature Communication. There he looks at how the length of the ligand affects the distance between the gold nanoparticles and so on. It is not I mean, naively, as a physicist, naively, I would think that, if you make it longer, the gap is larger, and you could really scale it with the length of the polymers. That only works for a certain size of the gold nanoparticles and then doesn't work very well anymore.
How does that affect your coupling effect, this light matter coupling?
So the light matter coupling depends essentially on the packing density. So whether you change the size of the gold nanoparticles or whether you change the distance doesn't really matter. The defining quantity is how much metal do you have inside a volume and how much vacuum or polymer do you have inside a volume.
Yeah, that actually leads to my second question.
Yeah.
For this interlayer couplings, right? So what you measure is that you always form this FCC structures.
Yeah.
And you measure this interlayer around 1-1 directions, right? So that's a close close packing direction.
Yeah.
Whether if you measure from other orientations, like say 001 or 110, do you think that's also going to affect your interlayer couplings?
It will not affect the interlayer coupling, but it will affect the dispersion because if we go, so right now we go along this gamma L direction, so that is a typical 1-1-1 growth direction. If we would go along gamma X, for example, that's 001. But for that we need to cut the crystals. And I mean, we have started discussing with people who do focused ion beam milling.
Or the calculation result, right? You don't have the experimental.
No, we don't have the experiments yet because you need to cut a lamella out of this crystal and then put it down and do the measurement. So it's not extremely straightforward.
Self-assemble different ways to control the orientation of the growth.
I mean that so if we use these large monodisperse gold nanoparticles, they always grow along the 1-1 direction of FCC. Yeah. I mean we do have where we saw a difference was this one here. Yeah. So the cesium chloride structure, we can clearly see that we also get these peaks due to the plasmon polaritons, but they are different frequencies. Yeah. And then we could then trace that back to the change in the dispersion of the plasmon polariton because we have different crystal structure.
Okay.
Maybe a last question. Sorry. Actually, you had a question, right?
No, actually, he asked my question.
Okay, perfect. Emily, last question.
Oh, I had a question. So in the deep strong coupling regime, I was wondering what your thoughts were on the impact of, say, surface selection rules for, like a localized dipole emitter if, this would make, for instance, optically bright or optically forbidden dark modes more accessible. Do you foresee that having like a impact on like nonlinear optical processes?
Yeah, so nonlinear optical processes, there are predictions. For deep strong light matter coupling, they're mainly only theory, because that is really a regime that's very difficult to realize experimentally, or you have these experiments using superconducting qubits that can kind of mimic these type of Hamiltonians. And there is one prediction that you should actually get into a nonlinear regime that becomes deterministic. Yeah? So where you don't need high intensity fields in order to drive nonlinear processes, but that you get it even on a single photon level. Yeah? And we were super excited. When we read the paper, we thought, okay, that's the direction to go, until we realized that all the theory is done for fermionic systems of excited states. Yeah. So you have a transition, and then once it's excited, it's blocked, whereas a plasmon is clearly a totally bosonic system. I still think there should be very strong nonlinearities, and we also have some first measurements looking at third harmonic generations using these gold nanoparticle supercrystals. But currently, we are really missing the theory input on this part.
Okay, with this, let's thank Stephanie again.
I have a question regarding why the edges look brighter.
You mean here in this? Yeah. Because you have, so this is a dark field. Okay. You mean by this?
Yes.
Because it's pretty. So this is just a change in layer number 1.
Yeah, maybe. Yeah.
And here there are elastic scattering of light.
Okay, so this is just means that.
Yeah, it's a source of scattering.
She was in
Well, if it is very thick, it just looks. So this is transmission.
Some hour, very similar things.
Yeah, that's what I realized.
So transmission reflection scattering.
So you want to?
So in reflection, I mean, you can see that but you cannot really count them.
Sorry, but
That's perfect.
So the chemistry, the synthesis of the.
and I want you to know.
Yeah, in that respect, I mean, it's a bit unfortunate, but we're getting it for
Yeah, hi, you're so made it.
Yeah, was a
I have a question. Can you synthesize these particles? Because okay, so we have a problem. We try to study edge dislocations in two-dimensional solid.
Okay.
And we're extremely interested in the statistical mechanics at a large length scale. So we very much wanted to just look at the defect, but at a large length scale. So if we can do, say, this kind of imaging, and then we don't really care about the individual particle. We're only interested in the dynamics of the defect, but we want to see many of them at the same time. So
But that's So what's the landscape you want to look at? And
we want to look at 100 micron scale, but we want to look at the thousands of topological defects at the same time.
Sure.
So
We can.
So what we want is a monolayer of something like a 0.5, so something like 100 nanometer to 200 nanometer gold particle, but it was uniform and then monodispersed. We want to make a two-dimensional solid, and then we want to look at the dislocation. Okay, so
we can talk more. I guess.
All right.
I guess since you're gonna meet our colleague.
Yeah.
Right next to I can take you there.
Okay, good, Tim.
Yeah.
Connected, so
Yeah.
that's good.
Yeah.
I did.
No. Okay.
So I
I'll come see you at 6.
yeah, but I have this presenter. I don't know.
You
Somebody
can
gave it to me.
I will just take her to
Can just leave it here. Okay.
office.
Just leave it here.
Oh, this is a
From one of the support people here.
okay. So they're gonna grab it.
I think I'm gonna grab it. Yeah, let's just leave it here.
You gonna steal it?
I would need one.
Yeah. So you talked to Yasu, right? So you know what we're doing. He
Yeah,
showed you
yeah.
some of our data.
Yeah.
Okay.
It's very nice. Yeah, so I discussed with him. And my suggestion would be to do some FTTD simulation.
Welcome to Bank of America. This call may be recorded. To get started, please enter the last four digits of either your ATM debit card number or your social security number or tax ID. That's 4216. Is that right?
Yeah.
Okay, I couldn't match that to the phone you're calling us from. For security, you must provide required information to speak with an associate or use our automated service. So let's try this another way. Please enter your full card or account number or your social security number or tax ID now.
Oh my god! Why are you naked?
I didn't understand. Please enter your full card or account number or your social security number or tax ID now.
What happened? Nick, she's taking a long to come here. This doesn't make any sense. Like, how did
For security, you must provide required information to speak with an associate or use our audit. Thanks.
Why would I do that? Look, you're still fully dressed. What? You owe me.
for what?
I couldn't get another girl last night.
Welcome to Bank of America. This call may be recorded. To get started, please enter the last four digits of either your ATM debit card number. That's 4216. Is that right?
Yes.
Okay, I couldn't match that to the phone you're calling us from. I didn't understand. Please enter your full card or account number or your social security number or tax ID now. Thank you. In a few words, please tell me what you're calling about.
Deposit issue.
You're calling about recent credits to your account. Is that right?
Yes.
Okay, before we get started, you've been selected to participate in a brief survey to help us improve our automated telephone service. To participate, please say "Quick Survey" once you've completed your transactions. Here are your recent credits looking as far back as October 18th. At any time, you can say "That's enough" or repeat. On November 30th, a teller deposit of $5,000. Of this amount, $0 is available now.
That's
On
enough.
November
Contact the
30th,
representative.
I didn't understand. Please say "Repeat that" or press 1.
Speak.
Do more or press 2. Do a search or press 3. Or say "Main menu" or press star.
Representative.
You'd like to speak with an associate. Is that right?
Yes.
To get you to the right place, please tell me what you need help with.
Credit alerts. Credit issues.
Okay, I see a check you recently deposited has a hold placed. This hold was placed to protect you from experiencing returned checks and fees. Please note, Client service specialists are not permitted to release funds. Based on current information, the hold amount of $5,000 will be available for withdrawal and purchases on December 7th by 9 o'clock a.m. Eastern Time. This is the most up-to-date information regarding this hold and is subject to change. Would you like to hear that again?
Connect me with an associate.
You'd like to speak with an associate, is that right?
Yes.
Before I transfer you, if you or your spouse is currently a service member on active duty and you're interested in learning about how Bank of America supports the military, press 1. Otherwise, for all other service, please remain on the line. Please hold while I connect you. Your call may be monitored for quality assurance. We are experiencing high call volume and longer than normal wait times. For fastest service, please download our mobile app or visit bankofamerica.com to obtain account balance, recent activity, or to transfer funds. Please press 1. To avoid waiting and get account balance and recent activity now, please press 1. Otherwise, please continue holding for the next available associate. All of our associates are busy assisting other callers. Rather than wait on hold, we can call you back when you're next in line. If you choose to use this service, we'll place a call using auto-dialing technology to a number of your choice, including a cell phone. Please press 1 to agree. To hear more about what a callback is, press 3. Your number has been entered as 40149747117. If this is correct, press 1. To re-enter, press 2. Please speak your full name at the tone, then press any key.
Ursula Valerian.
Thanks.
You're here now. I just like seeing crunchy. I'm sorry I brought it. My husband had this thing to maintain more aspects of the hospital. You look at the best, right? Look, the more people say it, the more they believe it. But it's not true. Tiwa, it's not true. I love photo. I do. But he's going to be the last one I'll be having. Yes, babies are overrated. Sleepless nights. You don't even have hangouts. That one is a problem. I mean, they can't be that bad. Have you had any yet? Don't. Seriously? Maybe? Tiwa. Sorry, 1 minute, please. Excuse me. Will always be my best friend. I'll be in the night for at least a little while. So, hey, did how can you talk? What is it important? No, not really. Where are you? Sure. dragging me because I was begging him to come and help me. Oh, Tata, you're so fine. You're so cool. First of all, I don't need to talk like that. I'm so sorry. It's true. Just thinking girl, you were wasted. Do you know how many shots we had that night? Oh my god. Oh my goodness. Anyway, so funny about it. I already told you there's nothing. Sorry, you know way about it. I mean, I know you love him and you're trying to be strong and all of that. Relationships require more than enough to function. So, what happens when you're sitting in this office? Do you ignore him and walk by? Do you just say, hey, you know, I literally have to say I care for him. I'm just trying. I'm trying to stay positive. I'm trying to focus on. Like for instance, the senior principal was showing my department. Wait, are you thinking of reference? Why not? So I worked so hard. Don't you think that is a good? Surely I wish you that. Surely one. Yeah. You keep surprising me every day, girl. You go get that thing. I know. I really want it. Okay, so let me see. Okay. Hi, Mohammed.
Listen, Soliva, I know that this is a work environment. It's not professional. You know that this year is casual for me. It cuts me deep. And I am not asking you to change it or anything, but I'm just letting you know that I didn't expect this from you. I'm sorry. Baby, I am so sorry, and I will tell you every day if I have to. Whether or not it makes a difference, that's fine, but I never, ever meant to hurt you.
Look, Mohammed, I know that you didn't. You made a mistake that anyone, and big deal. We're colleagues. So can we at least be civil, cordial, friendly even?
Baby, listen, we are not students, we are not.
We were.
We were lovers. You were more than that to me, baby. I know that I need to give you some time, but I just want you to know that I need you to please give me another chance, baby.
Look, Mohammed, my department is working.
You didn't ask why. I told you. Baby, I could not stand lying to you. And I promise you that this thing with this girl was a mistake. It was a mistake.
Are you trying to make this a problem?
No, baby. I'm not trying to do that, but I just help but wonder if you're trying to punish me.
That is why I'm asking why you are making this about you. Look, Mohammed, we've had way too many obstacles our way. And maybe this was the one mistake that we needed to set us straight.
Baby, please listen to me first, please. Before you say anything. in class, baby.
Look, Mohammed, we're on a train that is headed nowhere. I promise you, this is not my story.
No, sir, it's not like that now. I still want to buy it.
Where your money?
I have the money. It's just that.
Look, we'll see. Don't give me that one. Money for and back for ground. I mean, say, if you don't get the money right now, I will stay this way, my shoe.
Okay, please, now, calm down. What you promised me?
Last time we say you get the money now why I keep out for you now?
I'll bring it tomorrow.
But tomorrow never comes. That's why you tomorrow come next day.
Oh, yeah, wait. Make I got the best of it and
You sure?
I go bring the money tomorrow now. Give her the money back.
Let me tap. I get another one. Just see the ones where I get now and they more expensive than this one. But no worry, just come here. Money for hand.
When you've got a tough case, Deloitte's GovConnect Child Welfare Solution helps you focus on what's important. Getting children and youth the help they need. In a world of increased demands and limited budgets, we can help you manage your cases, schedule follow-ups, and easily access information on the go. That means less time on administrative tasks and more time empowering better family outcomes. For more than 30 years, we've been a trusted partner to caseworkers around the country. With GovConnect, you can focus on the children. We'll focus on you.
Wow, seriously.
So let me declare that. Welcome, welcome.
Are these your friends first?
Yes, my friends, Lakuli and Shayo.
Shayo. Luckily, how are you? I didn't. Because we're going back to our downstairs.
She's not your back as well.
If there is this in the fridge, you should have. I mean, warm it and giving it to your friends. Anyway, you guys can take care of yourself. Yeah. Just for an hour.
We're even about to go. Let me escort them out.
Okay, see you guys. Bye, Mom. Bye-bye.
How you have it? It's blocking every day at work.
To be honest, it's more difficult than I thought. I'm trying to heal, and then seeing you every day is not helping at all. And I feel like just always just been so complicated with us.
I don't know talk about it. I know that you.
Thank you. And I know you truly have it. But anyway, how are you? And how are you coping? I was going to talk to you earlier about I was not sure was it good time or
Okay. can